Good morning, everyone. Uh, as civil engineering students, we need to learn a new module of engineering physics um, in Unit 1 of elastic properties of materials. Starting with the introduction, we will study the elastic properties of materials by underlining what is stress, strain, Hooke's law, elastic modulus, Poisson's ratio, stress-strain diagram, elastic potential energy. All these uh, describe the behavior of materials which can retain their original shape or size after deformation, means after a force is applied. And then to study the elastic properties of materials, there is an engineering machine which is called Baldwin hydraulic machine for tension and compression test. This is the useful machine that you will use in your practical activities in order to study these elastic plastic behaviors of materials. Then starting with the introduction, why do we need to study the elasticity or elastic properties of materials? Starting with definition, elasticity is a branch of physics dealing with how objects deform under load conditions. This means that how objects behave after applying external forces. This means that how a body can change the shape or the size when a force is applied. Then, as these changes in shape and size take place, internal forces in the object resist the deformation. Such deformation are usually elastic and don't affect the conditions for equilibrium. This means that if an object is elastic, after an external force is applied, the object retains its original size and shape. But if the object is not elastic, after applying a force, then the body undergoes what we call plastic deformation. It means the object cannot retain its original size or shape. Then why is elasticity useful? It is useful for analysis and design of load-bearing structures such as building structures. Here we have bridges, space shuttles, prosthetics, biological implants, and so this elasticity is useful in the characterization of different materials. As engineers, you need to study the structure and the size and shape and how materials deform before using them in construction buildings. Starting with stress, the deformation of solids is discussed in terms of the concept of stress and strain, where the stress is the quantity that is proportional to the force causing a deformation. This means that the stress is equal to the external force acting on object divided by the cross-section area, where the stress sigma is equal to the applied force divided by area, where the force is expressed in Newton and the area in square meter. And we know that 1 Newton per square meter is equal to 1 Pascal. All this means that the stress may also be expressed in pascals. This means that you may consider an object such as a spring or another solid object with initial length L0. Once and this body has initial cross-sectional area A0. Once a force is applied to the body, this force can extend, means stretch, can stretch this object, or it can compress the object. For the case of extension, of this body. The body will regain a final length L and a final area A. This means that if a force is acting on a solid object, the length of the solid object changes, means increases, and the surface area or the cross-sectional area decreases. Then this applied force over the area gives what we call the stress. Then the stress means that how engineers normalize the force that is applied to a material to account for differences in geometry. Then this is very useful for predicting failure conditions for materials. This means that you can test whether a material can support a given force, especially for the material that you can use to build bridges. And here, still in a intensive testing machine, we first consider a body with its original or initial length L0. Then in this diagram 1, no load is acting on a body. In diagram 2, there is a uniform elongation, means there is a uniform extension of the body once a force is acting, and the area is decreased, reduces. And then if you continue to increase the force here in this machine, if the force is further increased by pushing down this fixed by moving crosshead, here we have an upper part which is the fixed crosshead, and then we move this down moving crosshead by further increasing the force on the testing specimen of the material. Then if the force is increased again to the maximum load, we have the maximum extension, means the maximum length attained. And then in part 4 we have a neck. We have a neck because the force is maximum and the body starts to break. And in part 5 we have the fracture, means that the material fails. And after the material fails or is broken, then we need to put together all the pieces of the material and then measure the final length. Then the strain is a measure of the degree of deformation, means that how a material deforms once a force is applied. Still consider a solid object or a spring. Then with initial length L, let us say this body has the initial length L0, body has initial length L0, and once a force F is acting to this solid material, the length of this body extends from L0 to a new length, let us say a new length L. A new length L. And here we say that the strain is equal to the change in length divided by the original length of the material, where this change in length is equal to the final length of the material minus the original or the initial length of the material. And then the deformation per unit length is deformation per unit length means the strain, which is dimensionless, because the change in the length has the unit of length, and the initial length or initial size of the solid material is also measured in units of length. Then by taking a unit of length divided by the unit of length, you get a dimensionless quantity, which is the strain. And the strain is a measure of the degree of deformation. And here the strain is very useful in the determination of how much a material can deform before failure. And here we may consider two types of strain. for the solid material there is a tensile strain. The tensile strain is the strain obtained when the length of the solid material changes. Means here, if we apply, let us say we have a solid material like this. If we apply a force on this material, this material is initial length L0. If we apply a force on it, there is a change in the length. There is a change in the length. Means that the length changes, and this new size is the final length L, and here where we have this strain equals to delta L divided by L0, means the extension divided by the original length of the material. And here we may consider that the surface area of the material decreases when a force is acting on an object. This means that the new area decreases. If the area decreases, this means that the width also decreases. Then this decrease in width comes with what we call lateral strain. The lateral strain means the change in width over the initial width, where this delta W means the change in width equals to the final width minus the initial or original width of the material. Then, and here we have a negative minus delta W, because the initial width is larger than the final width. Then this dimension here is the final width, but this, from this point to this point, we have our original width. This is the original width. You see that the width decreases. If the width decreases, the cross-section area also decreases. It's the reason why the change in width is negative, and the strain is always positive. To keep the strain positive, here in this formula we need to take the negative of the change in width divided by the initial width. Then the next point to describe the elastic properties of material is the determination of what we call elastic modulus, or modulus of elasticity. And it is found that for sufficiently small stresses, strain is proportional to the stress. Always the strain is always proportional to the stress, and this constant of proportionality depends on the material being deformed, and this constant of proportionality is called the elastic modulus, and this elastic modulus is equal to the ratio of the stress to the resulting strain. This means that if we say the elastic modulus, actually called the E, equals to stress denoted by sigma divided by strain epsilon. Then there exist three types of deformation and three types of elastic modulus, and here if there is a change in length, we talk about longitudinal stress and the longitudinal strain. Then and the elastic modulus associated to longitudinal deformation is called Young's modulus. Means that the measure of the resistance of a solid to change in its length, where we have what we call longitudinal deformation. Longitudinal deformation. of the material. Second one, there is what you call shear modulus. This is a measure of the resistance to motion of planes of a solid sliding past each other, and the associated stress is called shear stress and shear strain. And here there is a change in this is called the tangential deformation. It means that a force is applied tangent to the surface. This is called tangential deformation. Tangential one. Because a force is applied tangent to one of the surfaces of a solid object. Tangential deformation. We'll describe it later. And the last one is bulk modulus. This is a measure of the resistance of solid or liquid to change in their volume. Then here we have a change in volume, and the applied stress is called volume stress, and the strain is called volume strain. Then describing this modulus of elasticity step by step. When a body changes in the length, let us say that here we have a body with initial length Li, and a force, once a force is acting on this body, but to extend it or to change its length, then there is an extension in delta L. Then the Young's the modulus of elasticity in a length is called Young's modulus, and the Young's modulus denoted by the letter Y is equal to the tensile stress divided by the tensile strain, and the tensile stress is equal to the applied force divided by the cross-section area, and the tensile strain is equal to the change in the length divided by the initial or the original length of the material. And this is a very useful formula that we will be using in calculations. Then the modulus of elasticity, this modulus of elasticity also verifies what we call the Hooke's law. The Hooke's law is a representation of the stiffness of material that behave elastically. A material which behaves elastically is a material that which retains its original shape and size once a force was applied to it. If you apply force to a spring, we may take examples of elastic materials such as rubber material. If you apply a force to a rubber material, after applying the force, then the rubber material will retain its shape and size. Also the spring. These are examples of perfectly elastic materials. But there are other materials after a force is being applied to them, the material is distorted. It means is broken, and which means that the material cannot retain its original size or its original shape. Those materials are called plastic materials, not elastic ones. Then for elastic materials, the Hooke's law stated that this elasticity, or means the modulus of elasticity, is equal to the stress divided by the strain. Then the modulus of elasticity is how engineers characterize the material's behavior, which is very useful for knowing how materials behave, material selection for device design, and calculating the stress in material, since it is easier to measure the deformation than it is to determine the exact force on a material, which is very useful for civil engineering students and or civil engineers in a determination which materials to be used at different levels in their constructions. Then there is also what you call Poisson's ratio. When a body is extended, then its length changes, but its width decreases. And here we have the original length of the material L0, and from here to here we have the final length of the material after a force is being applied. We have L, and here we will determine what we call this tensile strain. The tensile strain is equal to delta L divided by L0. But this material has an original width. The original width of this material is determined from this side to this side. This is the original width. Then once a force is applied, the width of this material changes and becomes small. Then from this side to this side we have the final width, and here we consider what we call lateral strain. The lateral strain is equal to the change in width over the initial width. And here what we call the Poisson's ratio is the ratio, let us say the later on, it is the ratio of lateral strain over the tensile strain. Then here we put a negative sign because this change in width is actually negative. It is actually negative because the initial width is larger than the final width. Then to make this lateral strain to be positive, and this Poisson's ratio to be positive, it's better to put a negative sign in front of the lateral strain because the lateral strain is actually negative. And then here for different materials, for metals, the Poisson's ratio is 0.33, for ceramics 0.25, polymers 0.40. Then this is very useful in order, before using the materials or such as metals, ceramics, polymers, you need first to calculate the Poisson's ratio, and if it is near the given values, then the material can be used for different applications. Then there is also what you call the shear modulus, or also called the elasticity of shape. Then here the shear modulus is when a force is acting tangent to the body. Here we first consider a solid object such as this book. This book has this down part which is fixed. This part is fixed, and the upper part is free. Then we have a fixed face which is down, and we have a free face with above. Then we apply a force on the free face. Then the force is acting tangent to the surface, tangent to the force. Then this force which is acting tangent is called the tangential force or the shear force, and the obtained stress is called the shear stress, and the shear stress is equal to the shear force divided by the cross section area, means the ratio of the tangential force to the area A of the face being shared. And the shear strain is defined as the ratio of delta x. Delta x is the extension in length divided by the height of this solid object. where delta x is the horizontal distance that is being sheared, and the h is the height of the object. Then the shear modulus is equal to the shear stress divided by the shear strain, where the shear stress is equal to the tangential force divided by the area of the sheared face, and the shear strain is equal to the horizontal distance of the sheared face divided by the height of the object. Then the bulk modulus is the elasticity of volume, or what we call volume elasticity. This is applied to especially liquids and solids. Then once you apply a force on a solid object or a container of liquid, first the volume decreases. If the volume decreases, we have a change in volume which is negative, means the final volume is larger than the initial, is smaller than the initial volume, and the volume strain is equal to the change in volume divided by the initial volume, and the volume stress is defined by as the ratio of the normal force acting to the body divided by the area. And here we talk about bulk modulus, which is equal to the volume stress divided by the volume strain, and it is equal to minus the change in force divided by area over the change in volume divided by the initial volume. We actually know that the ratio force divided by area is equal to the pressure. It's the reason why the bulk modulus is equal to the change in pressure divided by the change in volume over the initial volume. The change in volume over initial volume is called the volume strain. And here we have a table showing different values of Young's modulus, bulk modulus, and shear modulus for different materials such as aluminum, brass, copper, crown glass, iron, lead, nickel, steel, and so on. And we may study the elastic behavior of materials by considering the stress-strain diagram. We first plot two axes, where horizontal axis is the strain axis and the vertical axis is the stress axis. For different materials, once we are studying their elastic behavior, first the material may behave elastically, or the material may behave plastically. Then for elastic materials, once a force is applied on the material, first when the force is increasing, the deformation also increases. Then once the force is released, the material retains its original size and shape. And but if the force is increasing and the material doesn't retain its original shape or its original size, the material undergoes what we call the plastic deformation. And it's the reason why here we may define two types of materials, where two types of materials where we consider materials which are elastic, perfectly elastic materials, perfectly elastic materials, perfectly elastic materials, and plastic materials. and the plastic materials. As explained, perfectly elastic materials are those materials which retain their shapes and size after deformation, and the plastic materials are those materials which cannot retain their sizes and shapes after deformation. It means they undergo a fracture, means a break. Then if we consider this material under test, and tensile forces are acting on the material. Once the tensile force is acting on the material first undergoes an elastic deformation. If the force is increasing, there is a point which is called the yield stress, where the elastic range ceases and the material starts the complete deformation. It means in this elastic range, the material is in a reversible deformation. But once the material starts to deform completely, then in a completely deformation, then the material is under the plastic deformation. The force is exceeding the needed force to that material can support in order to retain its original shape. Then the material starts, if the neck, if the cross-section area decreases and you start to observe a neck, then the material undergoes an ultimate tensile strength, which comes with a fracture or a break in the material. Then this elastic range means that the material will return to its original shape once an applied load is removed, and the stress within the material is less than what is required to create a plastic behavior or a deformation or stretch significantly without decreasing the stress. And the plastic range means that the material is loaded beyond the yield strength. It means the material is supporting a heavy force. The material will not return to its original shape after being unloaded. Then it will have some permanent deformation. Then this point, the yield point, marks the beginning of the plastic deformation, which is the end of the elastic deformation. And this stress-strain relationship is no longer guided by the Hooke's law. You know that the Hooke's law stated that the elastic modulus is equal to the stress divided by the strain. Then this Hooke's law is applied to perfectly elastic materials, means in the first elastic region. Then in a plastic region, this law cannot apply. Then the yield stress here comes to express the minimum stress that causes the permanent deformation. Means the starting of the permanent deformation. This yield stress is also called the yield point or yield strength or elastic limit. Means as the stress increases, a point in the linear relationship is finally reached when the material begins to yield. From the starting point to the yield point, the material changes linearly. Means that as the extension increases, the force also increases. It means there is a linear change in strain versus the stress. And the ultimate tensile strength means that there is a maximum stress that the material can withstand. Means that the material feels a maximum force. And also this defines the beginning of the necking. It means the cross-sectional area of the material decreases significantly. If the cross-sectional area decreases significantly, then the material breaks. where we have the fracture. We have the necking here, means a localized decrease in the cross-sectional area of the material once the force is increasing. And after observing the neck, there is a fracture, means a break in the material, which means that there is a force in which the material fails and breaks, and then the material can be studied for different properties. Then the elastic limit means that a point in where the maximum stress can be applied to the substance before the substance becomes permanently deformed. And there exist two types of deformation. There is an elastic deformation, which is a recoverable or reversible deformation, and a plastic deformation, which is a permanent deformation. And then this elastic deformation is reversible deformation, means when the force or load are released, the body returns to its original shape and size. It means the body retains its original configuration. In elastic deformation, this one, it can cause the tension. It can be caused by the tension or compression or shear forces. Then usually metals and ceramic undergo an elastic deformation, but at low strains. And there also exist two types of elastic deformation, where the elasticity may be linear or non-linear. Then for example, for aluminum, such as material aluminum deformed at small strains, as the strain increases, the stress also increases in the same range, means that the aluminum undergoes a linear deformation, but there are other materials such as the rubber, which undergoes non-linear deformation. The last one is the elastic potential energy. We know that the potential energy is the elastic potential energy is equal to the work done by applied force in deforming a body. This work is stored in the body in the form of potential energy, which is called the elastic potential energy. And we know that the work done is equal to the integral of the force times the displacement, when the displacement varies from 0 to the maximum extension x. Then we know that the applied force may be obtained from the Young's modulus. Here we know that the Young's modulus is equal to the stress divided by the strain. Then this is equal to the applied force divided by area, then divided by the extension. The extension means the change in length over the initial length. This means that this force F, the applied force, is equal to Young's modulus times the area times this length extension x divided by the initial length of the material. And then here we may replace the force here by this value. Then we multiply by the change in length. Then integral, we know that this Young's modulus, area, extension, and initial length, these are constants. Then If they are constant, we know that the integral of xn dx is equal to xn to power 1, x to power plus 1 divided by n plus 1. It's the reason why we integrate x dx, and it becomes 1, and this work done is equal 1 over 2 times the Young's modulus times area times the square of extension divided by initial length of the material, which means that as we see that the force is equal to Young's modulus times area times x over initial length, the work done will be equal to the half of the product of the applied force and the extension. If you are given an applied force and the extension, to determine the elastic potential energy or the work done during the extension, you will take the half of the product of the force and the extension. Or once you are given the Young's modulus, the extension initial length, and the cross-section area, use this formula. Then finally, the work done during the extension is equal to the half of the product of the stretching force times the extension. Then to find the elastic potential energy per unit volume, which is U in, means that the work done divided by the volume. We know that the volume is equal to the area times the length, means times the height. If we have a cuboid object which is extended, then you have such cuboid object, and you apply forces on this side and another force on this side. Then the length, this is the length L, and this is the surface area of the base. We know that the volume is equal to surface area of the base times the length or the height h of the cuboid. Then you see that here we have the force times the extension x, which is equal to 1 over 2 F over A times the x over L, where this A times L is the volume. This means that the work done is equal to the half of the force, the force times the x divided by the volume. Then here we have the stored elastic potential energy, or the work done per unit volume, is equal to the half of the stress times the strain, means force times the extension, which is equal to 1/2 of the force times the 1/2 of the force times the extension. And here the force over area is equal to the stress, and the x here, x is the extension here, x is equal to the change in length delta L, means the final length minus the initial length. This is the delta L over L is equal to the strain, which means that this potential energy or the work done per unit volume is also equal to the half of the product of the stress and the strain. Then if you have the stress and you have the strain, their products divided by 2 will give you the potential energy per unit volume. And here we have an example of calculation. The rod in figure below is exposed to a tensile force of 20 newtons and elongates by 0.03 meters. A. What is the stress in the rod? Calculate the strain, calculate the modulus of elasticity. We are given a body with height 3 meters. And the base has size 0.5 meters to 0.5 meters. This gives the surface area. We are asked to determine the stress. As an answer, in A, we know that the stress is equal to the force over area. The applied force is equal to 20 newtons. The area is calculated to be 0.5 meter times 0.5 meter, which is equal to 0.25 square meter. And the stress equals 20 newtons divided by 0.25 square meter, which is equal to 80 pascals. In B, we are asked to find the strain. The strain is equal to the change in length divided by the initial length. The initial length is 0.3 meters and the change in length is 0.03 meters. And then we have this strain is 0.03 meters divided by 3 meters, which is 0.01. And in number C, we are asked to determine the modulus of elasticity. The modulus of elasticity is given as the ratio of the stress to the strain. And as in A, we have calculated the stress to be 80 pascals and the strain from B to be 0.01. Then the modulus of elasticity will be equal to 80 pascals divided by 0.01, which is equal to 8,000 pascals. Then to get further explanations and read more, you may consider one of these books, especially book number 2. This is the most useful, beautiful book that you can read and understand. We will proceed later with exercises. Thank you for coming and following.